So where is forward on this? Is it? Okay, so first of all, I will try to learn the remote. First of all, thank you so much for the kind invitation to Bing and to Alison, who's helped me a lot with arranging the travels and coming here. I feel like a cousin from the countryside. I'm not so much into wood, but Bing asked me to talk about cellulose-water interactions, and then I became excited about that because that's one of my favorite topics. But when we talk about moisture interactions, what kind of material are we talking about? Are we talking about solid wood? Are we talking about the fiber wall? And this is an image of the fiber wall this is a native part, and this is a lignified. So where is the moisture absorbing, and how should we interpret that? This is also an image of the delignified fiber wall, where we are seeing the fibril aggregates and the distance between them. Is that where the moisture is absorbing? And also we'll hope to spend some time on models and the swelling of model materials of cellulose. And this is a regenerated cellulose bead that we have used for studies to find out what happens when you drop cellulose in water, when you immerse it in water. So, but starting with the facts that we have, that the interactions are necessary for plants. Cellulose-water interactions are necessary. They are necessary for paper making, for hygiene products and absorption materials. They're negative for the strength in moist environments, both for wood and more so for papers. Dimensional stability is a large issue. Of course, when moisture absorbs, you know that in composites that are not water resistant, they do swell and they cause a lot of problems. And dimensional stability is also another problem of the water. So the water is there, water is important, and the interaction is really important. And the form of water is important. So are we talking about vaporized water, or are we talking about water in the condensed state? And it's a very big difference. So this will be a combination of lecturing, and I hope you can take that. And it's well meant, and it's also giving some own results. But let's start by lecturing, and that is the driving forces behind moisture absorption to cellulose and fibers. People might find this as an academic battle, but it's not. It's a fundamentals that is important. And then factors controlling the swelling of cellulose when you drop it in water. And then also the state of water at the cellulose-water interface, some modeling work by others and some high-resolution measurements that we have done ourselves. And then what happens if you remove the last water from the cellulose? And these two last bullets has been catching our attention lately because they are important. The last layers are important, and they mean a lot for the properties of the materials that we have. So why and how does water absorb? Well, let's start by saying that it's an enthalpy gain that is a driving force, nothing else. It's the enthalpy gain when moisture absorbs to cellulose or to wood. And how can you study this? Well, it's the free energy of the interaction. You have the enthalpy and the entropy. And of course, when water molecules are leaving leaving the gas phase and depositing on the surface, they are releasing the heat of evaporation, and they're having the interaction enthalpy with the surface. Of course, they lose entropy. They're much more joyful to be out here than to sitting next to each other at the surface. So you lose entropy. And this has been studied over the years, and Professor Ishimaru mentioned that we had both read a paper from 1952 or something by Morrison, but there is also some other recent papers by Hollenbeck that it's very pedagogically written, and they combined calorimetry and moisture absorption, and by doing this you can sort out both the enthalpy and the entropy contribution for the moisture absorption. And I can really recommend it. It's nice reading. And what they find is that what you see here is that this is the cumulative part of at different moisture absorption, and you see that this is the free energy is increasing, And the initial part is the steeper, the gain or the release of heat is larger in the beginning than it is at the end of the absorption isotherm. And if you look, this is the cumulative one, and this is a differential part. So you see that up to a monolayer formation at the surface, this is from microcrystalline cellulose, there's a constant enthalpy change. And then as you pack more and more water there, you don't get as high enthalpy change. And you also see that the entropy loss is largest in the beginning. And this is the driving force. And let's say it's not the hydrogen bonding that is driving the absorption to cellulose. That's the fact. And there's also an interesting part, and that's absorption hysteresis. It's revealed both by absorption and calorimetry. So this is the data from absorption, and this is the desorption part. The reasons for this might be many, but in their conclusion is that it's both enthalpy and entropy causes. So the material might change during the moisturing on the cellulose, and this has been discussed by many others as well. But for the microcrystalline cellulose, the hysteresis is caused both by enthalpy and entropy upon absorption, not by swelling. And if you have fibers fibers instead of MCC, the situation might be a bit different. So what do we learn? Well, the enthalpy gain is the driving force for getting moisture onto cellulose. The absolute values can be then correlated to hydrogen bonding, of course, once the molecules are at the surface. And the surfaces are uniform. It's not specific site absorption. So they do absorb at the surface, but they just absorb, and then they can find their final positions. There is no specific binding sites according to this work. And I think Morrison says the same thing. And for this reason, we don't have any swelling. And at earlier times, use of calorimetry and absorption was tiring, and you had to build special equipment. Today, we don't have that excuse. We need money to buy the equipment, but there are excellent equipment allowing us to do these measurements today. So this is, I think, it's important. If we modify materials, we can study these details, and we should study these details. So what does this mean? Well, Lars showed some images of fibril and fibril aggregates. And I also showed some data from Jeff Daniels on my initial slide. But there's also a slide that has been a model that has been introduced. And we're talking about fibrils and fibril aggregates. We try to teach that. We don't have protofibrils and microfibrils and so on, but we have fibril aggregates. But if you say that we have fibrils and there are 4 × 4 nanometers and all the surfaces are available, you can calculate the specific surface area for a cellulose material, and that would be for pure cellulose, and that is around 667 square meters per gram. And if you then assume a monolayer coverage of water molecules, you end up with 0.33 grams of water per gram of cellulose, which is amazing. And then we have, so that covers the surface. I don't use any close packing or something like that. So this is what it brings to, and just a monolayer leads this to this amount of water. This is the back of the envelope calculation, of course. And then if we turn to swelling of fibers, then we say that how do fibers swell? Well, as you see here, this is in the image introduced by Aberson a long time ago. And we see that they introduced the concept of a multilamellar structure of the lignified fiber wall, where you have around 100 lamella for 4 micrometers. And all this can absorb water. And of course, that will cause dimensional changes, but fibers swell inwards mostly. And then we say that what is driving the swelling here is the pure polyelectrolyte type of swelling. So we have the free energy of swelling is the combination of the mixing term with water and cellulose, the influence by ions, and then you have the withholding forces by the network in the fiber structure. So how can we determine this? Well, for fibers, it's a nightmare, of course. There are so many fibers, in a couple of million fibers per gram in the lignified wood, and also they are basically all different. So what we have done is that we have developed a method where we regenerate cellulose. So we take fibers that we have carefully characterized and modified, we dissolve them, and we precipitate them under controlled conditions, and we get this astonishing beads, which is I'm very happy about this piece. I looked for this kind of materials for 10 years, and now we found that we can use cellulose to get these beads. We have spent a lot of time characterizing them. So we have done SAX measurements. So we know that they do assemble into larger aggregates that are separated by chains like this. This is a cartoon. Cartoons are difficult because they lock your mind. But this is how we have interpreted our SAX data. So higher charge has a bit different structure than we have with a low charge. And we have charged them to different degrees just to see the influence of the charges. We have looked at the swelling, and we see that the swelling follows when you increase the pH, you are dissociating the carboxyl groups, and you get an increase in swelling. And it behaves basically as fibers do, but exaggerated, of course, because fibers don't swell this much. And then we have these three terms, mixing term, the ion term, and the deformation term. And the ion term is rather easy. We know the charges, and we can estimate the charges from a simple osmotic pressure calculation like this. And then we use Flore-Hagen's theory to estimate the mixing term, and there we all naturally have the interaction term, the chi parameter, and phi is the volume fraction. And then we have the networks term holding these materials together, as in the fiber wall. But this is, of course, very difficult. So how we solve the problem is by estimating the chi parameter from Flore-Hagen's theory, theoretically, and then we determine the influence of charges, and then they have the ionic term. And then we determine the swelling under different osmotic stresses, which means that we dump polymers outside the bead and see how they deswell. So then we have three known, and then we have just the network term left, and that we can calculate. And there you see that we have the influence of the different volume fractions here. We see that the mixing terms, as you increase the volume fraction of cellulose, the mixing term becomes more important, and then you have the deformation term. The ionic term turns out to be, of course, much more important at lower volume fractions. Is this important for fibers? Is this something that shows something for fibers? Well, I've added the term here. This is how much a fiber swells, the lignified fiber in water. And you see that, yes, all these terms can play a big role when it comes to the swelling of fibers when you dump them into water. And we've done this. This is of course amorphous cellulose or non-ordered cellulose. So we've done the same measurements. We have done the same evaluations for filaments, endless filaments that we make by orienting fibrils under under specified flow conditions, and we see the same behavior. Not the same, but very similar behavior. So higher charge, a higher swelling, and at the higher charge, you get a deswelling due to the decrease of the ionic term. So this is what we have. So what we learn from this is that we can determine the fundamental properties from these measurements, and the effects that we see is that we have we have a flexibilization and increased conformability. That's very important. We have an increased surface swelling, which is important when you form fibers or fibers together. And you would change your swelling up with the fiber wall, and you have an increased availability of the interior of the fiber wall. So this we can quantify. We don't have to use hand waving, and that's the major message. Then there's the state of the water around fibers in the fiber wall. And that has been a question for many years. So how is the mobility of the water molecules affected in the fiber wall? And I wanted to highlight a number of, this is, okay, here's where the water is. And Lars Wagberg and T-Kiang Lee, they used relaxation NMR to see how water molecules relaxed if they are on the surface, if they are a bit from the surface, or if they are in the bulk, how are the movements changing? Lars Berglund, together with Istvan Fure and Jakob Wåhlert, they also did modeling of water around a fibril bundle like this, the fibril aggregate, where you have internal surfaces and you have external water. And what can we learn from this is that this is from the work by T-Kiang Lee and Lars Wagberg. And what they saw was that you have different kind of relaxation times. The tau F is the relaxation time of adsorbed water. The tau S is the relaxation time of water molecules that are diffusing between fibrils. And then the free relaxation time of water at 25 degrees Celsius is 2.4 picoseconds. So you see that the adsorbed water has a decreased relaxation, or they are slower, relaxing slower. And you also see that the water molecules that are hindered to diffuse inside the fiber wall, they are really slow. We are talking about nanoseconds and picoseconds. And they also saw, which is important, that there are 1 to 2 layers of water that are affected by the surface. So how am I doing for time, by the way? Is it? Yeah, okay. And then this work by Lars and Istvan is really enlightening, because they also model this by molecular dynamic simulations, and they see that there is in this fibril aggregate you have availability for water molecules, but they're very, very tiny layers that are adsorbed, and they are also, and then they have the free water molecules outside here, and there's a quick exchange between these layers. So so there is a change in movement of the water molecules tied to the close to the cellulose surface, and also there is a fast exchange of these different states. Otherwise, they would show up in scattering, for instance. If they would, so they are changing fast, they are slower, but they are exchanging. And this has also been shown recently by Jakob and his PhD student Alice Lelik. That they see that they have a change in mobility, and this is not the logarithmic scale. They have a change of mobility inside a pore like this, but you also see these are the number of water layers outside. So the conclusion is much in line with the earlier work by Wagberg and T-Kiang Lee, but it also shows the power of this kind of modeling when you are really asking the right questions. Lately, this has also been the drying of water molecules from the surface have also been studied by Igor Sosolenko and his group, and together with Lennart Bergström at Stockholm University. And they have been checking how easy is it to remove water molecules from fibril or fibril aggregates, fibril bundles, when you're decreasing the pressure outside. And you see that for non-modified, or for these sulfonated fibrils, then you can remove basically all the water. But for tempo oxidized, it's very, very difficult to remove the last water. So the type of modification will also influence how tightly these molecules are sitting at the interface. So very quickly, I would like to show you what is happening when you're removing the lost water. And from the this is from cellulose nanofibrils sheets. So we make sheets from nanofibrils. We dry them, and then we can change them to different salt to different count ions, because these are charged and contain carboxyl groups. And then we can heat them for different times, and then we check their reswelling. And we can measure the reswelling as a function of the count ion content, and we see that monovalent ions and multivalent ions play a very big role. And holocellulose is also something from Lars Berglund's group that we show that these are not modified, but they don't hornify to the same extent as others. So this is what we do, a more schematic treatment, and then we measure the reswelling degree. And then we see that when we heat treat this is the message. So when we heat treat the data to the sheets from 105 to 150, the swelling decreases, and there is a limit around 130 degrees. So after 130 degrees, we see a rapid decrease in reswelling, and also the counter ions plays a big role. But I will rush through this a bit. If you dry it in the protonated form, we don't see the big influence of the heat treatment, but we do see a hornification when we put them down in water again. So I think I'll skip a couple of slides and I'll go. We say that our hypothesis was that this seems to be like a diffusive process, a diffusive behavior. So we plotted the relative swelling after heat treatment as a function of heating time to the 1 over the heating time. We get a rather straight line. So it is some kind of diffusive behavior, but we don't know exactly what is diffusing. Our hypothesis is that it can be both molecules on the surface and water, but we haven't been able to separate this. So I think yes. The message there from that slide was that if you leave them in water for years, or for at least 1.5 years, they do reswell to some extent. So it's a slow process. But this was an important conclusion, is that we have, if we heat treat the fibrous sheets in the proton form, and then we for different times, and this is a wet properties. So these are wet sheets, and you see that they have a wet strength around 50 megapascals if you heat treat them. So if you heat treat them and drop them in water, they are really, really strong still. If you then change them from the protonated form to the carboxyl form, of course they lose most of it. So what we see with the hornification is that we take the last number of water molecules out, we bring the surfaces together, they get tightly bonded to each other, and when water molecule has to penetrate into this, it takes a lot of time. So we call it a kinetically locked state. And then what the interactions are at this interface here is still under debate. But we think that don't forget, we always state that don't forget the van der Waals interactions, because they are non-specific and they have a rather high range compared to hydrogen bonds. So what do we learn from these results? Well, we say that a few water layers is strongly associating with the cellulose surface. They have a slower diffusion compared to free water, but there is a fast exchange between the states. They are probably essential both when the tree is synthesizing the cellulose for the fibers to orient in the right way, and they also have an enormous effect on the mechanical properties of both wood, I would say, and for fibril-based materials. You remove this last layers, you have an irreversible association, basically irreversible. They can reswell. So the take-home conclusions and the final remarks are that the fiber water or cellulose water interactions have recently received a huge interest. And there are some enormous reviews out there, which are good to read. But if you want to read all the 1,000 references that the Eero Konttori has in his review, you have to study for a while, but never always read the originals. It's important to identify the critical questions when we talk about fiber or cellulose water interactions. And that is just because if you have to change something, you have to take the right method. A thin layer is important, as I mentioned. And an understanding how to control these layers is very important. And the hornification is something that you can turn into I'm not the first one to say it, but you can turn it into an advantage, not a problem, by using this controlled treatment. And the packing of all the last bullet, I think, is everybody who knows me knows that this is kind of not a religious convincing, but also a straightening up of the discussion. If you dump all your explanations into the hydrogen bonding bucket or swamp, you will solve very few problems, but you will bewilder the scientific community. But hydrogen bonds are there, no doubt about it, no doubt about it. So by that, I would like to thank again Liang Bing and Alison for inviting me and helping me with all the arrangements. Knut and Alice Wallenberg for a lot of financing for the work. The Science Council of Sweden, and also the Nils and Dorthy Troelsson's Forskningsfond Research Fund. That was Swedish, but I downloaded that from the net to give the right impression. And thank you for listening.
I just have a quick question. So the waters on the surface, the very surface of the cellulose, are they water? Are they formed in a water matter? Are they like almost like a crystal?
No. It's. They are slowed down. They are interacting strongly with the surface, but they are still. You still have picosecond relaxation times, so they are moving very quickly. And I don't think that they sit. If they jump into a hydrogen bond and say, "Yay, I'm home," they don't do that. They move all the time, but they are interacting with the surface. And if you look at the work by Morrison and by Hollenbeck, if you add the condensation heat and the heat of interaction, you can say that you are in the hydrogen bonding regime. But they are not fixed. No.